All right. Okay, good morning, everybody. I'm Christine Persson. I am the director of the Materials Project. I'm really happy and excited to open up the 2019 Materials Project workshop. I want to start with giving an immense thanks to the team, all the people in the blue t-shirts that have been helping you yesterday, and they're going to carry you through the next 2 days of learning about the Materials Project and its infrastructure, its data, and how to leverage it. I believe this is the fourth year that we're giving this workshop, and every year it fills up, so congratulations on making it and being early and registering. I was going to give just a little bit of an introduction, what the Materials Project is about, how it's growing, what kind of codes and data are available, and what may excite you about learning all the tools that you're going to learn about these 2 days. So I'll start with a very, very personal perspective on why first principles calculations are becoming commoditized, and most specifically why the data is becoming commoditized. When I started as a graduate student in Sweden a long time ago in 1996, I spent an entire year on calculating one property in one material, a whole year, to get the vibrational properties of tungsten, one element, a one atom unit cell. Because I had to fit the pseudopotentials, I had to parallelize the plane wave code, and there wasn't a linear response code that could do this for metallic elements, so one of the previous graduate students had written one and it needed to be adopted. So a lot of work on codes and infrastructure has led, and the fact that we now have high throughput computing, we have large computers that we can leverage, has led us to the point where we now, 20 years later, have hundreds of thousands of materials available on the Materials Project, with millions of associated calculated properties, where vibrations is just one of them. So for example, we have 1,500 full phonon spectra, not just for elements, but for binaries and ternaries on the Materials Project. And we're computing as fast as we can get our hands on computing. We have all these workflows that can do these things automatically, and it's really just limited by the amount of computing. So there really is a paradigm shift in how materials data are entering the design stream of material science. And whether you are an experimentalist or a theoretician, you should be leveraging this data, because it is out there and you don't have to be an expert anymore on running these calculations. You just have to be able to use the data judiciously. And if you're even better at it, you can learn to use machine learning and use APIs to download it. But basically it's there, and if you don't use it, others will. So this is an advantage. The Materials Project was started in 2011 here at the Lawrence Berkeley National Laboratory through collaboration with different partners. We raised our first large DOE Center grant in 2012, and we have promised to basically develop the codes to accelerate materials discovery and use those codes and scale them over high-performance computing centers to deliver data to ourselves, but also most importantly to the world, to disseminate that data in an easy and robust way for other users to use it, and to showcase design on a few examples. The amount of data that we produce is way more than what we could actually do design with. So that's the part where it makes sense to give this to the public. Why should other people recompute the same data in-house? It makes absolutely no sense. So if you give that data to the public, they can use it to inform their own calculations and then can do other calculations on top of that. Why should everybody recompute the silicon band structure, right? It makes no sense. Let's do it once and move on. A snapshot of some of the stuff that's available in the Materials Project that I hope you'll be learning about. Our code infrastructure that powers the dissemination and the production of this data. You'll learn about Fireworks, Pymatgen, and Atomate, and probably a little bit about Custodian. These codes, which all were designed and written in-house by the team, enable us to calculate data rapidly, robustly, with minimal manual intervention. And that gives rise to large data sets covering compounds, crystal structures, molecules, nanoporous materials, electronic properties, polar properties, mechanical properties, and now you can start seeing that if we fill this out, this space of different properties, we can start picking out materials with specific sets of properties for different applications, and we can get better at designing them. We have developed 14 apps to date, and apps basically take different amounts of data from different repositories and combines them in a way to give you a higher order analysis. So it gives you phase diagrams, Porbet diagrams for analyzing stability in water, band structures, reaction calculations, interface calculations, where again, hopefully you don't have to be an expert into how to run these codes, but you do have to know how to trust the data. How reliable is it? We developed the first materials API, and this API is so efficient now that we're delivering more than 1 million data records on average per day to the world. It has significantly grown in the last, I would say, couple of years, I think, because the whole idea of machine learning, and we do have enough data that you can actually start doing machine learning on some of these properties, has really taken off. You'll hear about MPContribs, which is our framework of adopting other people's data and connecting it to our data points, so really sort of becoming more of a hub for other people's data as well as our own produced data. I believe our number of users, which is growing exponentially, shows that the data is useful to people, that they are using it, that they understand how to use it. So we have over 2,000 people logging into the site every day. And I'll just give one very brief example on how you can use the data, and we're using the data to design novel materials, which is ultimately why I got excited about being a material scientist. Very, very briefly, the codes that power the materials project, again, Pymatgen is our input-output analysis code. It takes the raw output from whatever code you're running, if that's ABinit or VASP or NWChem, Gaussian or QChem, and turns that into engineering properties. The Fireworks code is our workflow code, and it basically allows you to make dynamic decisions during runtime. So if your VASP calculation or if your QChem calculation fails for a particular reason, you can take that failure output and analyze it against what is known in your database of these outputs. You can apply some fix to that, which you would do manually in normal cases, but this is now done automatically, and you can reroute and make dynamic decisions during runtime. Fireworks is completely agnostic to what code you're running. You could be running a finite element code for all Fireworks cares. It's all just is what you design it to do. But if you combine Pymatgen with Fireworks, which we've done in the code Atomate, you get recipe-based workflows for our first principles calculations. So Atomate basically allows you with a few lines of code and a submission command to run DFT calculations over a large computing facility. And lastly, our API, which powers both our website as well as for other people to draw large amounts of data from the website automatically, so you don't have to sit and click there on like 100 different band structures or whatever it is you want to analyze over large structure and chemistry spaces, and you'll learn about how to use that as well. This is the website. Probably you've seen it before. It's completely free. All you need is an email address to log in. And if you do, this is what greets you. It's sort of a little bit more of a complicated version of a Google of materials. And if you can add or you can screen for particular properties. If you want a dielectric material that has a specific band gap and you don't want to be too unstable and you don't want it to contain a particular element, those are the kinds of search criteria you put in here, and out comes a long list of materials that fit those search criteria. You can also go up in the apps, where again you get aggregated data from different compounds. For example, if you're looking at lithium-ion batteries, it's not just one compound, right? If it's an intercalation chemistry, you look at different amounts of lithium in the same structure. So that's aggregated data from different kinds of calculations. That gives you the battery explorer. You can explore those materials there. You can look at Porbet diagrams if you want to understand the stability of materials in water, or just phase stability in the phase diagram app. Again, aggregating data from different materials in the same compositional space. And you get then sort of analysis diagrams like this, Porbet diagrams. This is interfacial stability, for example, for heterogeneous catalysis or for solid-state batteries. And again, the battery explorer, where you look at oxygen evolution, which is a safety measure, and voltage curves. So again, aggregation of data over many different compounds. So if you then go in and click on one of these materials that fit your criteria, you want to explore more about it, you get its crystal structure, its magnetic ordering, its band gap, all kinds of structural parameters. You get its band structure with a warning saying that the semi-local DFT that we tend to employ here tends to underestimate the band gap. We're doing our best to inform our users on how reliable and how they should look at this data. No data is ever perfect, right? Whether you're an experimentalist or you're a computational person. So I know, shocking, right? So it's all about understanding your data and how to use it judiciously. So we try to do this, and there's also, for every single little field here, there's a little button where you can click and get more information, and then there's a wiki. So don't be afraid of clicking around and looking at all this. There's more than you think about information. Calculated XRD patterns, phonon dispersion curves with a really nice little interactive app where you can see how these phonos actually look in this structure, which is one of my favorite features. We have 500,000 K-edge Zane spectra in the materials project. L-edge is coming, X-edge is coming, so if you're excited about spectroscopy and understanding local structures in systems, this is a really nice feature, and you can also upload an experimental spectra and get an idea of what kind of local structure it matches in the materials project over a certain chemistry. Elasticity sensors. Substrate pickers, if you do epitaxial growth, this is a great tool for if you want to make a particular material. This gives you a list of ranked substrates that are more likely to promote this particular material in a certain direction than others. And it's at this point only going over what we call commonly used substrates. But if you actually know how to use Pymatgen, you can run it over any crystal structure in the materials project. Equations of state. Currently only over metals, but again, we have a workflow. We're hoping to do this for more materials. Similar structures, which is very useful if you have a structure and you like the structure for whatever topology is in there, but you want a different chemistry. Let's say you don't want it to contain lead or some toxic element. This gives you an idea what other systems there are that have similar structures, same kind of connection between different tetrahedra or octahedra, but has a different chemistry. Dielectric tensor. Piezoelectric tensor, if it's a polar material, and lastly, a calculation summary, which tells you all the gory details about how these properties were obtained. So, snapshot. Again, what makes me excited about being a material scientist, and today specifically about being a computational materials scientist and leading the materials project, is the fact that we can hopefully now use these tools and this data to accelerate materials design, to move from an Edisonian approach where largely you're relying on the intuition of a team. Where do we go for the next battery material? Where do we go for the next thermoelectric? You make a material, hopefully you made it, you test it, and you largely throw it away because it's really hard to find new materials that beat state of the art. And you keep going until maybe one day you're successful and you find something that's better. We can now use this data to pre-screen materials. So we don't have to spend so much time, because it's very, very time consuming still to make materials and test them. So to pre-screen materials, to come up with things that are more likely to be a good candidate and give those fewer selections higher probability to make a success story to our experimental counterparts, and then work with them to develop novel materials. I'll give you one example. We work with the Joint Center for Artificial Photosynthesis, which has one of its bases here in North California. We had a very short timeline to try to impress them because we weren't part of JCAP to begin with. So we had a year to sort of come up with potential new water-splitting oxygen evolution photocatalysts. We decided, because we had a short time, not to do the whole periodic table in every single crystal structure. So we limited ourselves to chromium, manganese, and vanadium-based ternary oxides, because a lot of binaries had already been explored. So what would you do if you are charged with coming up with a new photocatalyst? Well, just searching on, using the API and Pymatgen, just searching on the composition, like I can do any ternary oxide, but it needs to contain these elements. I get 3,000 entries, or I got 3,000 entries back in 3 years ago. So that's that takes a few minutes to make that search. Then I can use, again, Pymatgen to filter on phase stability. So using now the convex hulls of the materials project, the phase stability data that's already in there, and an estimate of the PB plus U band gap. So again, knowing what is the accuracy of PB plus U. This needs to be sort of expanded because we know we underestimate those band gaps, so we took a very, very wide window. We really want a 1.5 EV band gap here for optimal photo absorption, but we used a very wide window knowing that this data is likely to be underestimated and not completely accurate. Now we get 400. So here's where we actually start doing new calculations. All of this information is already available. No reason to recalculate it. Here we start doing HSE band gap. HSE is a slightly better functional, tends to get the band gap a little bit better. So now we can limit that window a bit more around what we actually wanted, so 1.2 to 3 EV. And now we get about 170 good candidates for possible photo absorption. Now we're down to a number where we can start doing band edge energy, so figuring out exactly that, or figuring out a guide for that the holes should have the right energy for this kind of reaction. And we also screen for stability in water. This data is already available in the materials project as well. I could have put it up here, and it would have screened out a lot of things already. This was just the fact that we weren't particularly smart. You guys should be smarter. So put this guy up here, and you'll get rid of some of these guys already, and you don't have to compute something. So it's about how to design your funnel when data is already available, knowing the accuracy of the data, and choosing your windows of screening judiciously. In the end, we came up with the magical number of 47. 47 was the number of things that are likely to have the right band gap for photo absorption, have stability in water, which is the operating media you want to be in, is likely to be able to be made, hopefully, because they are not too far away from the other stable things in the same composition range, and have the right energy of the holes that participate in the reaction. At that point, you talk to your experimental counterpart. So we had high throughput combinatorial synthesis expertise at Caltech. John Gregoire is a great partner. He was able to make 17 out of these 47 phases, and 16 out of them were actually working photocatalysts. So pretty good hit rate of giving. I'm not saying that all of them were great, but at least they worked to some degree, and some of them were actually quite good. So using this data in a way to design novel materials is clearly, and at least in this design example, not a bad idea. So I'll just end with this is one of the usage maps of the materials project. You can see that it's being used all over the world. There are definitely certain hubs in the world where it's used more, but what also makes me excited, especially being part of UC, and the fact that we just lost the Elsevier license to journals, is that in parts of the world where you may not have access to journals as much as we tend to take for granted in the US and other parts, the materials project is increasingly being used as a reference and lookup source for materials properties. We are getting the feedback and have been getting for a number of years that people love the materials project, but they want to contribute back to it. They want to not just use our produced data, but they want their own data that they're producing. They want to make sure that that also reaches our users and reaches the world in a more efficient manner than just publishing it or putting in the supplemental materials. So we've been working hard, and specifically Patrick has been working hard on developing something we call MPContribs and MPComplete. It's ways for anyone to contribute data back to the materials project. MPComplete is really just uploading a crystal structure, and we'll just put it in the queue, and it will run with all the other stuff we're running routinely. And it will come with your credentials, whatever you put on it. If this was a compound you came up with, you should put your publication in your name, and that's what happens. That comes up then as you are one of the you're the contributor of that material. MPContribs allows you to upload whatever data. If you have, carrier data, if you have spectroscopy data, and the beauty of it is that if you have any kind of information about the structure or the chemistry, we can then link that back to the organization of the materials project and expose that data to all of our users. So with that vision, I'll just turn it over to Donnie, and you'll be on your way, hopefully, to contribute and to use the exciting future of the materials genome. I should also say, do you have any questions? I'll be happy to take questions too at this point. Yeah.
So I'll just go back to your photocatalyst example.
Yep.
So it seems that materials project is great when we think about computing the average properties of materials. When you think about catalysts, a lot of the time what you're dealing with are like very specific surfaces or very specific sites
Yeah, no, that's a great question. So I would say that any design example, whether it's photocatalysis or batteries or thermoelectrics, you're going to need things on top of what I just presented. This gives you inspiration, maybe to go outside of the comfort space in terms of chemistry and structure, which most people sort of go like, well, if I'm looking for a battery material, I know layered materials are good, right? So I tend to sort of stick within the familiarity of spinels and layered materials. This could give you inspiration of going outside of that. On top of that, you're going to have to do exactly what you say. You're going to have to look at, are there defect structures on top of these different surface facets that will promote my catalytic activity? What sites should I be exposing? And how do those sites passivate or non-passivate under acid or alkaline conditions? And these tools can help you get there, but they are not going to get you all the way. So that's, I think, how you should think about it. It will help you identify new spaces. It will help you get identifying some structures that might be amenable, but you're going to have to do more detailed investigations after that. Other questions? Yeah?
Do you segregate between data you collected from simulations and collected from experiments?
If there is a difference or a separation, or?
Yeah, you can get for the same
Yep.
for the same property that you're trying to find. There can be an instance where you got something from simulation and something from experiment, and there's always some kind of difference.
Yep.
So how do you account for that?
Well, so when we develop our workflows, the first thing we do is actually benchmark against whatever available data we can find in the world for that. So for the elastic tensors at the time in 2014 and 15, we found 200 full elastic tensors measured in the literature. We benchmarked against all of them with our automated workflow, and we got within plus minus 15% of the reported experimental data. That was, in many cases, better than if you have two experimental measurements of the same material, because that in particular is a property that is very dependent on if you have an impurity phase, even a little bit of it. So in that sense, I would actually trust the experiment. I mean, we present them both in the paper to make in the end, the user should make the decision for themselves, and they should use this plus minus 15% as sort of at least that error bar compared to experiments. In other properties, I would say that the discrepancy is larger, and it's not clear where the error lies, either in the computations. In the band gap, for example, we're off, right? And we know that most of our functionals. I would say, from my perspective, we'd like to inform our users exactly what the difference is. When we have reaction energies on the materials project, we present whatever we have from experiments and computed side by side, so that people can make their own choices about whether one is reliable or the other one. Yeah?
This is obviously amazing stuff, that's why we're here. So you've seen an increase in user base, I'm assuming.
Yes.
As a director, where do you see Materials Project in
5 years?
5 years.
Well, if we're following the exponential growth that we've been enjoying since 2011, somebody can make that calculation where how many users we're going to be at in 5 years.
Use machine learning to figure it out.
Yeah, thank you. Honestly, the limitation right now it's on funding to keep this staffed up, which every software infrastructure needs staff and needs people to maintain it. I'm extremely fortunate that my entire group voluntarily helps out with this. So not all of them are funded for software infrastructure, but they do it anyway because they're so passionate about bringing these tools to the public. We're also, the fact that we have open source codes helps us. These codes are increasingly getting developers all over the world. So I hope the ones of you that like this and that you become part of our development team around the world and help us to grow these codes and abilities, and we'll all benefit from it. My hope is, again, that this will be used by everybody who does materials design. Whether you're an engineer in a company, it should be at the fingertips of anyone. That if you start thinking about new materials, your first thought should be, well, let me look it up in the materials project and see what I can find out before I do anything else. That's my very humble goal.